Okay, let's continue. This is going to be General Chemistry Part 27. Alright, and reaction continue Part 12. Alright, Part 12. Okay, now we are in the middle of conclude the final steps on one of the example in precipitation reaction. All right, we up here and then the tape cut off on me, and so we were talking about spectators. Now, the spectator are those species in the chemical reaction not actually participate the chemical process to form a product for that particular reaction, in this case a solid, and stay in the solution as cation and anion pairs. In this particular case are the ammonium and the sulfate. Alright, and we know that, if they are confirmed exactly the same, what we talk about exactly identical means their chemical formula, number one, should be identical. Number two, their charge, cation, positive charge, anion, negative charge, must be exactly the same, before and after, as reactants and as products. Number three, quite important. Now don't underestimate the importance of this physical states. Must be same as well. Aqueous begin with, end up with aqueous, right? That is case, only in this case, only aqueous, right? Because you talk about ionization of the compound species as reactants, and dissociate and ionize into cation and anion pairs. And end up with something, exchange partner become the products of double displacement or double replacement reaction become solid. But the remaining cation and anion not participating in that process become left off as identical ion pairs from the beginning of these two reactants. So they must have exactly the same physical state, not different. Then, number four, the coefficient, right, after the reaction equation is balanced, which are the mole ratio. The mole ratio of these cation and anion before and after the reaction, right, must be same as well. So we look at it. So for ammonium, we got NH4, that's the formula, number one. Number two, the charge plus one, both plus one, same formula. Number three, physical state aqueous. Number four, how many each side? 6. Then these two on either side of arrow, of course pointing one direction as irreversible reaction, are identical. Then we are able to cancel them out of the complete ion equation as spectators. Is that clear? Is that slow enough? Yes, okay. So then we call them spectators. Spectator means they are the onlookers. They are watching the reaction going on in front of their eyes. But they are not participating. Do you see my point? They're looking at it. Okay, that's what's going on over there. I'm not part of it. That's called spectator, okay? So now we are able to cancel. After we cancel the spectator on both sides of the equation, then whatever left off are the species actually the participants of the reaction, So then we are able to put them into one line as a net ion equation. Net means what? It's not a gross income. It's net income, right? Net means everything not important, we trash them, right? Leftover important variable, we keep them. So that is net ion equation right here. So the net ion equation are the calcium 2 plus cation, 3 of them in aqueous solution, started, and then the 2-phosphate 3- anion in aqueous solution, and then they combine into a compound with a solid insoluble, and is a calcium phosphate, the Ca3 subscript. In parentheses, we have PO4, and outside parentheses, we got 2 because we got double the PO4 in order to matching the oxidation states internally belong to the compound, and then show the compound outside 0. So this whole thing is 0 outside, but inside you have those charge, right? It's called effective charge, or we call them oxidation states. Right? All right, now this is the whole thing we are able to discuss, and then we try to understand it. Right now, last question: is this in the past we always represent certain reaction with certain example, right? And remember, if you recall in the past, and at the end we always ask, is this a redox reaction, right? We try to see if it's yes, if it's no, we make a strike, right? We did that. So what about this precipitation reaction? Was this calcium sulfate and ammonium phosphate? All right, is this a redox? Now remember, most of the case, double replacement or double displacement, right? Reaction, they are not redox reaction. There is no electron transfer or oxidation state change involved in the process. So they are not a redox. So let me put here the very last, not a redox reaction. If you don't believe it, you can double check with the oxidation state of any elements involved in this reaction, whether or not they have oxidation state changed before and after reaction. No. So it is not redox. Okay, now we finished. But just the end of this discussion brought us to the beginning, right? Brought us to the beginning of the last type of chemical reaction we call redox. Now let's talk about redox reaction. I need a space, so I have to erase the whole thing, alright? And so we can start. We don't want to talk too much. Why? Because we've been talking about redox reaction in the past. We've been involved in the redox reaction discussion in the past. Why? If you remember, we just said at the end of introduction of each, right, different type of reaction, we always ask to find out if that type of reaction could be redox. Remember that? And then we verified through a process by comparing the oxidation state of each different elements involved in the process, whether they changed or different before and after. Then we decide if they are redox or not, right? So we involve a lot of them. So here, okay, that's good enough. Now let's say that's number 8. Now on my handout, right? Oh, that's number 7, right? Number 8. All right. Redox reaction. Right. What is a redox reaction? All right. A reaction involves, or any reaction involves, right? Any reaction involves, let's put here, any reaction involves electron transfer between, and let me make clear, normally people don't put this in the definition. I want you to understand, electron transfer must be occurred between the elements of the reactants, all right, not between the reactants and the products. I will say why in the near future. Between the elements of reactants. Right? Or sometimes, or any reaction involve, or any reaction right, involves change of oxidation state on certain elements in the reaction. Let's put REXEN. Right. I don't have to put this in the reaction already. Right. Now, simply we say, if any involve transfer, now some are lose electron, become more positive, we consider that being oxidized, right? And gain electron, because the electron is a negative charged particle, you gain electron, your oxidation state must be changed towards the decreasing end on the number line. If we already learned that, right? We recall, right? So we can do this all the time. You know, this is for instance, right? So give some example. Now the simple one, if we are able to heat up some metal, right, and then, for instance, just talk about old time, the photographer used the flash, right? That time we do not call electronic flash, we call electric flash. It generates a high spark, and the current goes through the ignite a ribbon of magnesium, right? And magnesium is going to burn quickly in the presence of oxygen in the air, right? And plus, of course, in the air we have a large quantity of nitrogen. Magnesium is able to burn in nitrogen form nitride as well, so generates so much heat and the bright lights. That's the flash. So the photographer is able to use that flash to give a artificial lighting to the object and take picture with a good exposure. Good picture. That's for the reporters, for the photographers, right? Catch the moment, right? And that is the reaction some of the author, Peter Atkins, consider that's called a corrosion reaction, which is, I call it just simply composition or synthesis reaction, because we combine magnesium metal strip and oxygen gas forming oxide, right? So magnesium strip, right? Magnesium strips, all right? Ignite, right? Under high current, high electric current, high electric to burn in the air with oxygen gas. Right? So that's the situation. So we have magnesium. The magnesium Mg, right? Mg. Now as we learned, magnesium metal is solid, and we also mentioned in the past, if elemental, right, elemental species, for instance, metal, non-metal, their oxidation states are considered as zero, right? Even they form any diatomic, triatomic, polyatomic, right, molecules like hydrogen gas H2, chlorine gas CO2, right? Each of those atoms of the same element, their oxidation states are also zero, right? So magnesium metal strip, the oxidation state, what is it's going to be zero, right? It's going to be zero, right? All right, then you ignite it by the electric current, very high voltage, right? That's generated, and the spark, and then burn the magnesium strip in the presence of oxygen. Then oxygen will be a gas. Now that's a diatomic molecule, so it's zero, right? It's also zero oxidation state. But then it is a one-way street, all right? Form an irreversible reaction called magnesium oxide, right? Which are also solid, right? Now this is not considered as a solid formation because it's a white powder. If you remember or have ever watched a movie about old time, use that kind of a flash, big, semicircle ball was going to burn, and then the refractor. That's a refractor, and the shining lights. Now, for instance, there's a movie called Lady in Red, right? Let's talk about the gangster John Dillinger, right? Was killed by FBI in Chicago outside the theater, and then the informant who was considered as his girlfriend, and then helped FBI point out what she was with Dillinger, and they walked out of the theater after the movie, and then she's supposed to wear the red dress, and then she's supposed swing her skirt or dress at the time, and the FBI agents and all the machine guns point to Dillinger, killed him. Now then that very moment, I don't know if that happened or not, I think that happened. There's a lot of reporter around and took picture afterwards, and then took picture after Dillinger's dead on the ground, was in the blood, and not all the bullets right in his body. So that kind that's a flash we talk about. Those are powder. When you boom, took picture, smoke come out. The smoke's what? Magnesium oxide, powdery, and I would have sat down, but it's heat and it's going up, right? Hot, going up. So that's now this kind of reaction. Is this a redox? Let's check it out, right? Zero. What is that? Now it becomes a compound, the binary compound, right? Binary compound, magnesium is going to be what family? 2A, right? Alkaline earth metal, right? 2 plus. So inside is a +2, and then this is oxygen always -2, and then if it's separated, it's going to be 2 plus and 2 minus. Inside oxidation state, it's going to be +2 and -2. Of course, they become. So there is, yes, it is a redox reaction. Why? Electrons seem to be transferred. Now who's who? From who to who? From who to who? The stuff from zero become positive. On the number line, let's put a number line here, right? So number line we did a couple times. It's familiar with you. Now we have a 0 in the middle is neutral, and 1 minus, 2 minus, 1 plus, 2 plus, and we don't need more because that's only 2, right? So both stuff from neutral, magnesium, solid, then oxygen, and gas, correct? Now after reaction, they burn, right? Energy released, right? They put energy in there to burn. After energy getting to, start to initially collision of those two elements was their atoms, and then they form bonding. The bonding formation always, most case, involve large amount of energy be released, right? Then the compound magnesium oxide will be much more stable than before, because that's higher energy, it's lower energy, right? For this whole system. So magnesium from 0, right, become what? That's magnesium end up with here. Now if we go to the right hand side, that means what? This arrow means oxidized. That's the direction. Here is reduced. Well, it's decreased, right? Decrease means reduced, right? So this is going to be reduced. Now, so magnesium from 0 to 1 is being oxidized. Is that clear? Alright, and then the oxygen, let's see, use top. Going this way, right, the oxygen, right, 2 oxygen. We are not talking oxygen 2, we talk 2 oxygen atoms, right? Magnesium atoms, let's say atom. And oxygen atom. Alright, let's make sure this is clear, alright? This is not going to confuse you. Alright, we're not talking molecules, we talk atoms. Each one gain from 0 to 2 minus gain 2 electrons. So 2 of them, right? You got 2 of them. Let's say 1, another 1. Let's do this. Is that better? Okay. So total number of electrons the oxygen atoms require to change its oxygen state from 0 to minus 2 is going to be what? 4 electrons. Where do those 4 electrons come from, right? And so come from 2 magnesium metals. So here is not yet balanced. So what happened is reduced. So oxygen, here is the oxygen atoms being reduced. Right. Let's make it a little bit, it's too crowded. Alright, let's reduction this side. Reduced. Now, if the magnesium being oxidized, right, electron being taken away, right, and then those electrons go to somebody to do something. What is that? To reduce somebody, right? So the magnesium atom being oxidized and then to become a what agent? Reducing agent. Right? Then the oxidation, oxygen atom being reduced, and then to become what? You tell me. An oxidizing agent. Because it takes somebody's electron out of them into himself, and then time somebody lose electron to you, you become a oxidizing agent because you're taking electron out of somebody being oxidized, and you do this job to oxidize somebody, so that somebody lose electron to you, alright? But number of electrons will be exactly the same. Here, let's see. Regularly, we are able to balance this equation by what? Using my tips, right? Using my tips. But now we are able to do this balance equation by using the number of electrons being transferred as well. So here, let's just use the old way to see if we have the mass balanced, right? Magnesium 1 on this side, magnesium 2 on this side. It seemed like a balance. On my notes, I did this, right? Okay, magnesium, right, is 1 to 1, right? 1 to 1. 1 to 1 is okay. Right? The first step's 1. Right? That's okay, right? That's okay. That's 1 to 1, right? Now oxygen. Oxygen 2 to 1. Oh, this is 2. So this is 2. Right? Then I have to multiply this, right? No, it's not big enough, so I double this. So I'm going to double this. Now I've got 2 oxygen, correct? But then if you double the magnesium oxide, the magnesium atom become double. It's no longer balanced. So because I've got 2 magnesium on this side and only 1 this side. So now what happened? Magnesium has to be double checked and redo it by what? Multiply by 2. Now it's done. So you have 2 in front. Now I said that mono-elemental, single one element, those species, we better leave it alone. We double check. We can redo it. It won't affect anything else because it's owned by itself. It doesn't have oxygen combined. So if you this need 2 and this about double, it does not change the previous balance process, and the balance reaction equation is still valid, right? So now it's balanced. Now that's the way. That's the old one, right? Old way. Then that's the way we talk about regularly. And then if we're using the electrons involved, right? Now, one magnesium can only offer what? Offer 2 electrons to 1 oxygen, correct? So 1 magnesium offer 1. But here we got 2, right? We got 2. 2 oxygen atoms require 2. Total 4 electrons. So 4 electrons. So we've got to double this, right? So each one offer 2 electrons from 0 to plus 2, right? Remember, alkaline earth metal, second family, right? It's all plus 2. So you 2 each one offer, so you can take care of 2 oxygen atoms. Now, so the 2 each and 2 oxygen atoms, and then you have to have 4, right? And then if you have this case, then this has to be doubled, right? So you have to double this. Now you have a 4 electron, and then out of a 2 magnesium atom, and then these 4 electron goes to 2 oxygen atoms, right? And that is balanced. Right? So in this case, 2 electron per magnesium atom is not enough. You have to multiply by 2, so give you 4 electrons to what? To reduce, right? 4 electrons to what? To become reducing agency to reduce oxygen, to reduce 2 oxygen atoms from 0, right? 0 to -2 each. Right. All right. Now, how do we represent this kind of change with chemical reaction? We now involve a new concept called half reaction equation. Normally we call half redox reaction equation, involve the electron as a participant in the chemical reaction writing. Now then we involve C, half redox reactions. Right. Okay, time is up, and then we continue this, and then in the part 27, next section. Let's start.